Looking at section 3.2, part 2, we're going to look at graphs of exponential and logarithmic functions. So it tells us to graph f of x is equal to 3 to the x, and g of x is equal to the log base 3 of x in the same coordinate rectangular system. So it says first we set up the table for the coordinates of f of x is equal to 3 to the x, and this should look familiar because it's the same example that we did back in section 3.1. So if we take and we plug in a -2, that means that we're taking our 3 to the -2 power, which means that we have a 1 over 3 to the second. 3 to the second gives us 9, so we'd have a 1 over 9. If we plug in that -1, we're taking 3 to the -1st power, which again is going to give us that 1 over 3 to the 1st power, which is a 3, so we'd have our 1/3. If we have f of 0, anything to the 0 power gives us 1. And if we take 3 to the 1st power, we're going to end up with 3. So we know how to make a table of our basic exponential functions. But what happens when we get into our logarithmic functions? Now, hopefully at this point you understand that the logarithmic function is just the inverse of the exponential, which means all we're doing is taking our x and our y values and we're reversing them. So it says we are going to reverse the coordinates for the inverse function, g of x is equal to that log base 3 of x. So when we had our -2 for our x value, our -2 is now our y value. That means that our x value is going to end up being a 1/9. So when we had a -1, we're going to have a 1/3. When we had a 0, we're going to have a 1. When we have 1, we're going to have 3. And we could have continued this on a little bit more. Sometimes it's nice to have just one more value on this table. So if we were to plug in 2, the value of the function at 2 would be 3 to the 2nd power, which is 9, which means we could also have this other ordered pair that would give us a 9 and a 2. Again, all you're doing is taking that exponential, figuring out what your x values and your y values are, and then you're just reversing or inversing them with your x and your y for your logarithmic function. So if we were to take these two pieces, these two tables, and plot some of these points out, I'm going to take and graph out our regular exponential function. I'm just going to use some colors. I'm going to use pink. So f of x was equal to 3 to the x. We're just going to graph that the exact same way that we would have graphed it back in section 3.1. So we were at -2. At -2, we were at 1/9. At -1, we were at 1/3. When we were at 0, we were at 1. And then that extra, when we're at 1, we were at 3. And then that extra point I kind of threw in there, that 2 would have taken us all the way off of our graph, kind of up there at 9. So that's going to give us that exponential function that, again, we had looked at back in section 3.1. I'm not going to hit that point very well, but that's okay. So that gives us our f of x is equal to 3 to the x. And then all we're doing to graph that logarithmic function was graphing that table that we made, which was inversing or reversing our x and y values. So that means, I'm going to do this in a lighter blue. If I were to graph my logarithmic function, I'm going to look at an x value of 1/9, and I'm going to have a y value of -2. That means I'm going to end up going over to 1/9, which is not very far off of that 0, and I'm going to go down to -2. So at 1/9, I'm down at -2. At 1/3, I'm going to be at -1. At 1, I'm at 0. At 3, I'm at 1. All I'm doing is getting these numbers right off of this table up here. I just kind of already have it in my mind. And then I have that last one, 9/2, which would be all the way out somewhere up crazily over there, right? So that's going to give us this function that, if you notice, right, as we kind of come in here, this is going to get as close to 0 as possible, but it's not going to touch it. If you remember with our exponential functions, we had a horizontal asymptote at 0. We're now going to have a vertical asymptote at y equals 0 when we go to a logarithmic function. So just some other little characteristics to point out. Speaking of our characteristics, let's take a look at our characteristics of our logarithmic function. So number 1, it says that the domain of f of x of our logarithmic function consists of all positive numbers from 0 to infinity. Well, if you look at that graph, that last one that we did, right, that blue function, we are looking at starting at 0 and we're going off to infinity, right? So we now have a domain that is going from 0 to infinity. And the range this time consists of all real numbers. Our range going up and down. There's no limitation up and down to that logarithmic function. Number 2 says that the graph of all logarithmic functions of the form f of x is equal to log with that base b of x passes through the point 1, 0, right? Again, that's that inverse. Our logarithmic went through 0, 1. Our exponential went through 0, 1. Our logarithmic is going through 1, 0. And that says because the value of the function at 1 is equal to log b, 1, is equal to 0. So the x-intercept is 1, and there is no y-intercept. It says if b is greater than 1, f of x is equal to log with that base b of x has a graph that goes up to the right and is an increasing function, just like what we just looked at. It says for part number 4, if b is in between 0 and 1, meaning it's a fraction, f of x is equal to log with that base b of x has a graph that goes down to the right and is a decreasing function. And number 5 says that the graph of f of x is equal to log base b of x approaches but does not touch the y-axis. The y-axis, or x is equal to 0, is a vertical asymptote. So our exponential had the horizontal, our logarithmic has a vertical in terms of that asymptote. So a little bit more information about the domain of the logarithmic function. It says the domain of an exponential function of the form f of x was equal to b to the x indicates all real numbers, right? So if we have our exponential, our domain was all real numbers. That was negative infinity to positive infinity. And its range is a set of positive real numbers. Our range was starting from 0 and going into infinity. I guess that'd be more. I was working on some algebra 2 stuff. I don't really want these as squiggles. I want these as parentheses. Sorry about that. So our domain and our range of our exponential, right? And then it says because the logarithmic function reverses the domain and the range of the exponential function, we're going to be able to say this time that our domain is going to end up being from 0 to infinity, our positive real numbers, and then the range is going to end up being those all real numbers from negative infinity to positive infinity. So it says in general, the domain of f of x equals log base b of x consists of all x for which g of x is greater than 0. So here's a little key here. Domain, it says that it has to be greater than 0, right? Because we now have that vertical asymptote that's occurring at that x equals 0. So an example, it says finding the domain of a logarithmic function. So find the domain of f of x is equal to log, this is a base 4, and then we have an x minus 5. It says the domain of f consists of all x for which x minus 5 is greater than 0. Where is that coming from? This piece right here, in terms of our domain, our input values, what can we plug in for x? It tells us up here that that g of x function, this piece right here, has to be greater than 0 because we have that vertical asymptote at 0. All of those values have to be greater than 0 value, which means to find our domain, we're going to solve out this quick little easy inequality right here. So if I were to solve that out to get x all by itself, I would get rid of that negative 5 by adding 5 over, which means that x has to be greater than 5. So then it says we found that the domain of f is, well, if it has to be greater than 5, that means that we're going to start at 5. And where are we going? We're going to go to infinity. It says this is illustrated by the graph of f. So they give us kind of the picture of what that logarithmic function is going to look like. But now we're going to have this vertical asymptote that's occurring at x is equal to 5. So it says that all points on the graph of f have x coordinates that are greater than 5. Some other things with our logarithms, we have what's called a common logarithm. It says the logarithmic function with base 10 is called the common logarithmic function. If you didn't realize this yet, the majority of the math that we do, the majority of life around us, revolves around a base 10. And why does it revolve around a base 10? Look at your two hands. How many fingers do you have? You have 10 fingers. Why do you think we use a base 10? Because you have 10 fingers and it's easy to count by, right? So the common logarithmic function is going to use a base 10. So it tells us that the function f of x is equal to log with that base 10 of x is usually expressed as f of x is equal to log x. So you do not need to write in that 10 here. That is what is going to be your common logarithmic function. It's going to be assumed that it is a base 10 if it doesn't give you that value at the bottom. Kind of just like when we take a square root of a number, we don't have to write that it's a number 2 on the outside there like we do when we take a cubed root, because as soon as you see that root sign, you know it's a square root. It's kind of assumed. So same thing with our common logarithms. So if you don't have a 10 or a number written there as that base, it's assumed that it's the common logarithm, which is the base 10. Let's look at an example. It says a percentage of adult height attained by a boy who is x years old can be modeled by f of x is equal to 29 plus 48.8 log of x plus 1, where x represents the boy's age from 5 to 15. Once a boy hits 15, typically he's at the point of not growing too much further beyond that. So you can't throw like a 25-year-old in here and kind of assume that he's still growing. So then it says, and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has the boy attained by age 10? So they give us a function and they're telling us that we're looking at age 10. That means all we're going to do is wherever we see our x, we're going to plug in a 10. So that means we're going to solve out what happens with 29 plus 48.8 log of 10 plus 1, which means we really are going to have a log of 11. So if we were to take and plug that into a calculator, hopefully you have a calculator somewhere you can just kind of grab and double check. I'm going to use my fancy smancy keypad over here that I have. All right, so if we have a 29 that's going to add with that 48.8 log of 11. Let's see if it does it correctly for me. All right, so we get about a 79.81. So approximately what percentage are we looking at? We're going to look at approximately 80% of his adult height is going to be obtained by age 10. All right, so if you want to write that in there. Approximately, we had a 79.82-ish, I guess. All right, some properties of our common logarithms. Just like we looked at some of our exponentials when we went into the our logs, we are going to look at some of those common logs. Very similar. So the general property says log with that base b of 1 is equal to 0, right? Remember, that was the same thing as looking at a b to the 0 power was equal to 1. That base to the 0 was equal to 1, right? It's going to be written out just as a log 1 is equal to 0. If you have a log base b of b that was equal to 1, that's where we had kind of that idea that b, the base b to the first power, was equal to the big B, right? Log 10 is equal to 1, right? Because it's a base 10. If we have log base b of b to the x, that's just equal to x. Remember, that was kind of the idea that the log with the b and the b, they all kind of canceled out, and you're just left with that x. And same thing, we have a log 10 to the x is just going to equal x. And then number 4, we have that b log base b of the x. Again, that was the kind of stuff that looks like it just in that sense canceled out to just leave us with the x. Those are those kind of special cases. They are called inverse properties. They kind of undo each other, right? So number 4, the 10 raised to the log of x is just going to equal x. The other type of log we're going to have is what's called a natural logarithm, or the natural log. So it says the logarithmic function with base e is called the natural logarithmic function. So it says that the function f of x is equal to log with that base e of x is usually expressed as f of x is equal to ln of x. So instead of using a log with that base e, they're going to go to ln. And I'm not sure if you saw that relationship or not on your calculator, but if you remember when we started talking about this number e and we looked on the calculator for that e raised to the x power, that was right above that ln button. So ln and log are both located on your calculator, right? This one's going to be used for the natural logarithm. And where you might see this more often is actually electrical engineers will use base E a lot more often than that basic log, base 10. So again, some of those properties that we have looked at, very same thing, right? Almost the exact same thing as what we just did with the logs, right? All these same things, except it takes it into looking at the ln instead of just the log. So that those are all going to have that base of e for the natural logs. Okay, same type of concepts if you want to look over them. And the last example we're going to look at, I believe, it says when the outside air temperature is anywhere from 72 degrees to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. This is why people have a fit over people leaving their dogs in their car, right? And they're like, oh no, the window's not cracked. The temperature in a car is going to raise really fast. So it says that the function f of x is equal to 13.4 ln x minus 11.6 models the temperature increase, f of x, in degrees Fahrenheit after x minutes. It says use the function to find the temperature increase to the nearest degree after 30 minutes. So again, this is just a calculator problem. We're just going to plug some numbers in and make sure that we know how to use our calculator. So in this case, we're talking about 30 minutes, which means that all we're going to do is in place of x, we're going to plug in 30. So the value of the function at 30 is equal to 13.4. You're going to use that ln button and then type in the 30. And then we're going to subtract the 11.6 and we'll see what we get. I'm going to try to, again, use this little calculator that I could just kind of type it out. And hopefully it works out okay for us this time. All right, 13 doesn't like me yet. Delete that. If I have a 13.4 ln of 30 minus 11.6. Looks good to me. We have a 33.97. So that's going to be approximately, we'll call that about 34. So it says that the temperature, get rid of that real quick. The temperature will increase by approximately 34 degrees after 30 minutes. Now think about that. Your car is sitting somewhere when the outside temperature is from 72 degrees to 96 degrees. In just a half an hour, it's going to raise 34 degrees. Don't leave your dog or your child or your little bratty brother in the car all by themselves for too long, because that is not going to be a good thing.